Okay, welcome to the set theory seminar. So today we have Corey Switzer. He, as you all know, got his PhD at the Graduate Center in CUNY, and currently he has a postdoc in Vienna. And yeah, he's talking about projective well orders and other beautiful pathologies.
All right, great.
Go ahead.
Thank you so much for everyone for coming, and thank you also for the invitation. It's always really great to come speak at CUNY, of course. Though usually I think when I talk at CUNY Talks, I say, oh, it's nice to visit New York or some joke like that. But I feel like because today you're actually in the classroom where I teach, I feel like in some sense you're coming to me now and not the other way around. And as part of that, you get to experience the Viennese culture of I have to clean the board every time I use it. And you also get to hear the really bad jokes that I tell my students while I do it because I don't know what else to say. So you're welcome. Anyway, everyone can hear me okay, yeah?
Yes,
all right,
very good.
Cool. All right, great. So yeah, the name of my talk is Projective Well Odors and Other Beautiful Pathologies. I gave a talk at VCU a couple of weeks ago where I talked about sort of a more introductory version of this information, because you try to give a wide audience talk at VCU, and I called them quote unquote weird sets, and Vera in the question session was sort of jokingly giving me a hard time saying it's not nice to call them weird because this is what we do and whatever, and she suggested I call them beautiful, so that's the name. But sort of what's the setting? What are we kind of talking about? So just to give a very brief, probably mostly incorrect version of the history, it's well known that the axiom of choice implies all kinds of sets of reals that you wouldn't just find them like on a walk in the woods or whatever. And in particular, sort of the classic example is that it implies, of course, that there exists a well ordering of R. We don't really know anything about this well ordering. It's not clear what it should look like. And a kind of, I think, natural question that I guess goes back to the beginning of set theory, it was probably asked by Suslin or maybe even Cantor, is what is the sort of complexity, which now we think of in terms of descriptive set theory, of a well ordering of the reals, some order which I can think of as a subset of the plane. Okay, and so the first result in this regard is essentially due to Sierpinski. I think it's like this. So Sierpinski proved this assuming continuum hypothesis, but it's not hard to generalize it, and you get it without any additional assumptions. So he proved that a well ordering of the reals is never Lebesgue measurable. Essentially, basically the same argument tells you that it never has the bare property or the perfect set property or any of these kind of regularity properties. And in particular, analytic sets are Lebesgue measurable. So well ordering the reals is never it's never analytic or co-analytic. And in particular, not Borel. Let me just say also, I think I forgot to say it, but because I'm going to be actually moving for once, I don't know how much I'll be able to monitor the chat. So if you have a question, please shout it out. It's never co-analytic, right? And so just as a remark, by the totality of the order for any of a well order, I mean any linear order, for any n, so a well order, it's sigma 1n if and only if it's pi 1n, and so if and only if it's delta 1n. because, to say x comma y is not in the well order just means that y comma x is in the well order. So the best that we could hope for is that we could have a delta 1, 2 well order of the reals. And you can. So this is, I believe this is actually due to Gödel. I think I read that. Someone can correct me if I'm wrong. So if V equals L, then there's a delta 1, 2 well order of the reals. Just as a remark, this doesn't explicitly say anything about descriptive complexity. And so, for example, if you have enough large cardinals in your universe, or determinacy axioms, you'll get that there's no projective well order of the reals or whatever. And so having something like this is a sort of anti-large cardinal hypothesis, which of course this is as well. So there's something sort of nice there. Okay, and I want to just very vaguely sketch the proof of this because the same ideas are going to come up again throughout my talk. So I'm not really going to go into any details. There's an enormous amount of coding, which I'm not even really going to mention. But the idea is that you have this canonical well ordering of the reals. Canonical well ordering of the universe if V equals L. So if V equals L, there's this canonical sigma 1 definable well ordering of the reals, well ordering of the universe, sorry. For me, the reals are the universe, so that's my confusion. Which I'll always call less than L. And then the point is that for, say, Cantor space, or any perfect Polish space, X is L below Y if and only if, because it's sigma 1, for every limit ordinal alpha, L alpha will correctly compute this. If it has X and Y, of course. And because every real appears by L omega 1, every real appears in some countable transitive model, which itself can be coded by a real. So X is L below Y just in case there exists some L alpha, to put it sort of crudely, so that X and Y are in L alpha, and L alpha thinks X is L below Y, where this is really shorthand for it's a model of this sigma 1 statement, which again, because it's sigma 1, it has to be correct for some limit ordinal alpha. And so by essentially condensation, L alpha, you can sort of code it by a real. All you need to say is that it's well-founded. I mean, the real is isomorphic to it will be, you just have to say it's well-founded, which is a pi1,1 property. So you're saying that there exists an X which satisfies a pi1,1 property. And then it's an observation of Solovey's that if I have two reals and I want to say that they're in some structure coded by another real or a Borel set or something, that's pi1,1 in the codes. So I have existential and then pi1,1, pi1,1. And then now I'm only quantifying over what's going on inside my model. So that's arithmetic, because remember, this is really coded by a set of reals. So elements of it are natural numbers. Sorry, it's coded by one real. So delta 0, I don't know, arithmetic. So that's how you get a sigma 1, 2 definition. And then the point is just by this totality remark, sigma 1, 2 implies delta 1, 2 for a linear order. Okay, so that's what's going on there. And the proof relativizes in a sort of obvious way. If V equals L of X, then you have a delta 1, 2 of X well order of the reals. And actually, there's a kind of surprising converse to this. So this is a theorem due to Mansfield. So if there is some delta 1, 2 of x, well order of the reals, then every real is constructible from x. So it's not just that you can't say that it's v equals L of x, because maybe I could add some, you use forcing to add some subset of some very large kappa, and that won't affect this. But every real is constructible from x. It's a very nice argument. So if you're like me and you're interested in cardinal characteristics and the structure of the reals, you might want to sort of ask, well, what about, what can I say then in sort of more interesting models of the reals than just v equals L of x? For example, if I want the continuum hypothesis to fail, what can I expect, right? So the best possible, it's no longer delta 1, 2, it's delta 1, 3. And this is consistent. So I think, so this is due to Harrington. I actually think this was his thesis. So it was published in 77. So it's consistent that Martin's axiom holds and the continuum hypothesis fails, and there is a delta 1, 3 well order of the reals. Okay. But Martin's axiom kind of implies that all of the cardinal characteristics are big. The structure of the reals in some sense looks a lot like under CH. And a lot of other work was done in this area that I'm going to skip through. And then what I want to talk about today is a theorem from 2009, which is due to Vera Fischer and Cy Friedman. So they prove that it's consistent, or let me say it like this. So they start in a model of L, and they prove that there's a forcing notion forcing P such that P forces, first of all, that the continuum is Aleph 2, and there's a delta 1, 3 well order of the reals. And I know I only have a little bit of room down here, but otherwise I have to stop the theorem to erase the board, so I wanted to squeeze it in. I'm sorry. So there's a well order of the reals, and P has the Sachs property. So if you don't know what that is, I'm not going to tell you right now, but it's a property, it's an iterable property for proper forcing notions, which implies essentially that most cardinal characteristics stay small. So actually in this model, basically all cardinal characteristics are small, so it's very not a Martin's axiom model. So they prove this, that it has the Sachs property, and then they also prove that, I'm not actually going to write this down because it's not necessary, that this is an iteration of length omega 2, unsurprisingly. And you can actually weave into the iteration other iterands you might like. So they prove that actually you can get sort of all kinds of different cardinal characteristic inequalities consistent with this delta 1, 3 well order of the real. So it's a very flexible way of forcing this nice well order. And I'm sort of going to revisit this model today. Is kind of my plan, and talk about some new work.
You meant delta 1, 3, didn't you?
Yeah, is that not what I wrote?
No, but you said 2, as I heard.
Yes. So I meant delta 1, 3. I wrote delta 1, 3. Yeah. All right. So let me erase the board here. I can leave this up so you can look at it. Yeah. So this model this paper is from 2009, and a lot of work has happened since then. But the kind of motivation for this project, which is what I'm going to follow up talking about, is that also in L, and this is an observation that's essentially due to Arnie Miller from the 80s, there are lots of other sort of quote unquote pathological sets that have optimal complexity definitions. So if V equals L, Miller proved that you have a co-analytic MAD family. And it's a very well-known theorem of Adrian Mathias that there are no analytic MAD families. So that's best possible complexity. If V equals L, you have a co-analytic maximal independent family. And again, there's no analytic maximal independent family, and many other sort of things like that, where these quote unquote maximal sets that require or seem to require the axiom of choice. And in fact, their non-existence is consistent with the failure of the axiom of choice. So to sort of summarize what I said while I was erasing the board is, so I'll put it in scare quotes because it's not formal. So if V equals L, there are many optimal complexity sort of extremal sets, and the kind of front of the book example is a co-analytic MAD family. And so the question that Vera asked Jeff and I, so this is joint work with Vera Fisher and Jeff Bergfalk, I'll say in a second when I get to our results. But the question that Vera sort of asked us when we started working on this is, what happens in this Fisher-Friedman model that I mentioned? So what about in the Fisher-Friedman model? What complexity do other extremal sets have? So these beautiful pathologies in the title. And it turns out that we can kind of get all of them of optimal complexity. So as I said, this is joint. This is now the sort of main result of ours that I want to discuss, the new one. So this is joint with Jeffrey Bergfalk and Vera Fisher. So we proved we couldn't work directly with the forcing that they used. We had to kind of augment it a little bit, and we kind of augmented it in a way that I think is sort of interesting. And a big part of this talk is going to be to sort of show you what that augment is and why I think it's sort of different. But let me just give you the theorem. So it's consistent that the continuum is Aleph2. There's a delta 1, 3 well order of the reals. And so there is simultaneously, so there's a pi 1, 1, hence optimal complexity, MAD family of size Aleph1. So optimal complexity, optimal size. So in particular, the cardinal characteristic A is Aleph1. There's a pi 1, 1 ultrafilter base. of size aleph 1. So the cardinal characteristic U is aleph 1. And again, this is optimal complexity. You can't have an analytic one. And there's a pi 1, 1 maximal independent family. Of size aleph 1. So again, this cardinal characteristic I is aleph 1. So we get a sort of, I think I wrote in the abstract, a maximal model of minimal complexity. And there's other things you can put here. We sort of stopped because we felt like the point was made. Okay, so this is kind of the main theorem, and then you know we have some strengthenings and things which I'll discuss at the end. But this is the main theorem that I kind of want to go over. I talked about this at Lumini, and Vika, when she invited me to speak, said that I guess some people would like to see more details. So I'm going to try to give enough details to really understand what's going on in this proof. And honestly, the goal, more than anything, is to describe this Fisher-Friedman forcing in our variation, which, you know, some of it, a lot of it is old, but I think it's really beautiful, and I think there's some cool things about it. So I'm happy to talk about it, and I think it's probably not so well known. So first, I want to describe sort of our modification, which is minor. This Fisher-Friedman forcing. And then I want to show you, so the way we proved all of these is we constructed, so the ground model here is L, and we force over it. And we constructed sort of special witnesses to each of these, which could be preserved. And we proved these preservation theorems that ended up being sort of odd. And so I want to give you the example of the MAD family and describe what's going on there, sort of to show you what's going on. And then probably by then I'll have gone way over time, and I'll just wave my hands at this if I even get there. But so describe preservation of pi 1, 1. Okay. So that's the sort of plan. And now you get to watch me clean the board again. So there you go. Are there any questions while I'm doing this?
Is it conceivable to have say an ultrafilter base of size aleph 1 and for 2 the aleph 0 to be bigger than aleph 2?
I mean, it's conceivable. I mean, okay, here's the issue. So like the way that you would try to, so if you want to blow up the continuum above aleph 2, which you can do with a delta 1, 3 well order of the reals, the easiest way to do this would be with CCC forcing. I mean, it's hard to make the continuum larger than aleph 2 without CCC forcing. If you do a finite supported iteration of CCC forcing, you're going to add Cohen reals, and Cohen reals will destroy ultrafilter bases. So you have a problem there, and I don't know whether this has been solved. So my guess is that it's probably open, unless someone wants to. Yeah, I mean, one thing that I'll say is once you have a delta 1, 3 well order of the reals, you have sigma 1, 3 witnesses to a lot of these things, just because you can replace the application of the axiom of choice by the explicit well order. Sigma 1, 3, pi 1, 3, depending on what it is. Okay. So let's see. All right, so I want to spend probably the majority of the rest of my time just describing this Fisher-Friedman poset, because it's complicated and there's a lot of interesting ideas in here. And it's going to be a countable support iteration of size aleph 2 of S proper posets for some specifically chosen stationary set S. And let me just quickly remind you what that means. So if you take a stationary subset of omega 1, then P is S proper if basically the normal definition of properness, so for all countable elementary submodels, theta sufficiently large. But I want that the intersection of omega 1 with M is in S. So instead of a club of models here, you just get a stationary set of models. Then everything else is sort of normal. So for all P in this M, there exists a Q stronger than P, which is an MP maximal, MP master condition. So however you want to say it, Q forces that M of G dot intersect V is M, or whatever. You know, it's a generic. The generic is generic over the little model. So this is properness with this extra condition, and there's kind of a sort of standard example of a forcing which is S proper but not proper. And this is kind of ingredient 1 in the Fisher-Friedman poset, 1 of 3. So if I have a stationary set, co-stationary set S, so both eta and its complement are stationary. Then I can look at the forcing notion Q of S. Depending on who you talk to, it's either Q of S or Q of omega 1 minus S. But this is how it was in Vera size paper, so we use the same notation. So this is the forcing. So conditions are closed bounded subsets of the complement of S. So C closed bounded. And the order is end extension. So what this does, if you force with this poset, it shoots a club through the complement of S. So it kills the stationarity of S. It preserves the stationarity of the complement. And in fact, it preserves the stationarity of any stationary subset of the complement. And it's omega distributive. And that's your example of a S. I guess in this case, this would be an omega 1 minus S proper poset. So it's omega 1 minus S proper. And it's a sort of classic fact. I think this is maybe due to Jensen, that it adds no new omega sequences of ordinals. And in particular, it adds no new reals. And we're gonna apply this club shooting forcing to a particular family of stationary sets that you define in L. So lemma. So you prove this sort of the same way that you prove that diamond holds an L. So there's a sequence S alpha alpha less than omega 2 of almost disjoint stationary subsets of L. Sorry, subsets of omega 1, excuse me. Almost disjoint here means that the intersection of any two is not stationary. So there's a sequence like this, which is sigma 1 definable over L omega 2. Yeah. So for all suitable models, I haven't given you this definition yet, but all sort of nice enough transitive models of ZFC. I'll give you the formal definition in a minute, but let me write this down first. For all suitable M and N of some nice fragment of ZFC. If they agree on omega 1, so these are transitive models, they have some ordinal that they think is omega 1. If that ordinal happens to be the same, then they actually agree on this sequence on their common domain. So then, how do I say it? So S alpha from the point of view of M of the alphas that are in both the omega 2 of M and the omega 2 of N equals the same thing for N. This is not so important. The sort of cartoon thing to take away here is that it's sort of sufficiently definable that anytime I take two sort of nice models, they're going to really agree about what's going on here.
Corey, could I just ask
yes.
you, do you use the diamond sequence to define these? Like,
yeah, I believe so. Yeah, to be honest,
yeah.
I haven't looked at this proof in a long time. This is in Vera and Sai's paper, and they even sketch it and say it's quote unquote well known.
I see. Because I mean,
yeah,
I guess you could just, like, if you look at the canonical diamond sequence in L, and then for every subset of omega 1, you can just look at on which points it is guessed. That gives you such a sequence of stationary sets. So maybe that's.
I think that's exactly what they wrote in, in their paper. Yeah.
Okay.
So there you go. Yeah. Okay. Cool. And so if moving forward, I'm just going to fix one of these. I mean, sigma 1 definable in some sense is the most important thing here, and actually almost disjoint. And then I just also want to fix some stationary subset S, which is almost disjoint from all S alpha, all these other ones. So for example, I could let S be this S0 and then just shift all the indices over by 1. That would be fine. But this is the S which our post set will be S proper for. Okay, so while I'm erasing, let me kind of tease what will happen next. So the Fisher-Freeman post set really, there's sort of a couple different parts that are all in the service of coding enough information that we ultimately get a nice definition of a well order of the reals. And the purpose of these stationary sets and this club shooting forcing is that this gives me a somewhat canonical sequence of Aleph 2 many objects. I know that I want my reals to be of size Aleph 2 in the extension, and I have names for all of them. And basically, as I go along the iteration, if I discover that, you know, I want X to be below Y in my in this well order I'm building, I'm going to shoot clubs through certain of these stationary sets so as to sort of code X less than Y into this stationary non-stationary pattern. Now, of course, that's not a thing on the reals, but this is the sort of first step of coding our well order into the stationary non-stationary pattern. The next step, the thing I hate about this is they put this here, you put the chalk on it, then you wash it, and then the chalk is wet and you can't use it anymore. I don't understand this. So the next step, they call a localization poset. I wish I had a really simple explanation for what this does. You'll see at the end, it's hard to explain off the bat. But the setting for the localization poset is suppose we're that V equals L of G star for some G star generic for some poset P, which is an L, and P preserves cofinalities and hence cardinalities. So we're in some cofinality cardinality preserving extension of L. And I fix some subset X of omega 1. And I have some sentence phi with parameter omega 1 and X, which is sigma 1, 1. Sorry, sigma 1, excuse me, in the language of set theory, the Levy hierarchy. Then my forcing notion, this localization poset, is called L of phi. And it consists of all functions R from, I'll call it the domain of R to 2, such that the domain of R is a countable limit ordinal. R codes X on its even parts. So, how to say it? So for all alpha less than the domain of R, alpha is in X, if and only if 2 alpha, I guess, let's say, R of 2 alpha is 1. So the interesting stuff is happening on the odds, but also we're going to pick up a code for this X. And sorry, for some reason I keep forgetting to write down this definition. So let me finish this and then I need to give you this definition. The awkward thing about giving slide talks for 2 years and then trying to go back to board talks is the slide talks, they tell you what order to say things in because you can't change it. The board talks, you can accidentally skip a step. So I'm sorry about that. I'm out of practice. Anyway, so for all, here's this word again. So gamma less than or equal to the domain of R. And for all M, which is a countable, suitable model, so that if I look at R restricted to gamma, it's an element of M, and gamma is the omega 1 of M. Then M thinks that phi of gamma comma X intersect gamma holds. So if I have this element for my condition sort of in this nice enough model, it's going to be a sort of promise or a witness that M thinks the right thing. It's modeling this sigma 1 sentence. And ultimately, this sigma 1 sentence will basically say something to the effect of, we coded, a certain piece of this well order we're going to build into the stationary non-stationary pattern of that sigma 1 sequence of stationary sets I told you about. All right, so let me give you.
Corey,
yes.
Just thinking about this sequence of stationary stationary sets. So the reason why you singled out this S0 or you fixed one stationary set is that you wanted to make sure that that one gets preserved. Is that the idea? So right. You're going to be, so to speak, S0 proper the whole iteration?
That's exactly right.
Okay. All right.
Yeah, right. I mean, of course, if you're not careful and you're shooting clubs all over the place, you could shoot them through disjoint stationary sets and then, well, you collapsed your life. So yeah, that's exactly right. Okay, so let me, before I forget again, let me give you this definition of suitable. So a structure M is suitable if M is transitive, it satisfies some nice fragment of ZF minus, say. It thinks that omega 2 exists. And the omega 2 that the ordinal that M thinks is omega 2 is the same ordinal that M thinks its L is. Sorry, L from the point of view of M. Okay, so for example, L omega 3 is a suitable model. Any Moskovsky collapse of a countable substructure of L omega 3, elementary substructure of L omega 3 will be a suitable model. And if I take cofinality preserving forcings of those things, again, suitable. All right, good. And then there's one more ingredient that I need. I know it's sort of a lot of notation, but I hope that I haven't already lost you all. Okay, so the third one is kind of the most interesting one. I guess I didn't say. Sorry, let me, really out of practice with this. Let me say, what is the point of this forcing? Excuse me. So lemma. For every gamma less than omega 1, the set of conditions in my localization forcing whose domain is greater than gamma is dense, right? Of course, what am I really trying to do here? I want to build a characteristic function of a new subset of omega 1. It's not obvious from this definition that you can always extend as long as you like, but you can. I'm not going to prove that. It's in Vera and Sai's paper. Right. So if G is generic, then I can look at Y as the union of G. And if M is a suitable model, and it contains Y restricted to the omega 1 of M, then M thinks that this sigma 1 sentence phi holds of gamma M thinks that, right, of the omega 1 of M comma X intersect omega 1. That's not a misprint. It is X. Right? This is sort of what happens here, right? This is what this condition is telling you. So we get a kind of total subset of omega 1 that if M has like the right piece of it, then it has to think this sentence. So it's a way to ensure that enough good models think the right thing. And then the last thing is that L of phi has a sigma closed dense subset. So it's proper and it adds no reals. So the last ingredient in this forcing is the only part that adds reals. And ultimately, we want to build a well order on the reals of a nice complexity, which means that no matter what kind of witnesses to this well order, if it's all this stuff that's on omega 1 and omega 2, somehow all of that has to get coded into a single real, or coded into many reals that we can then refer to in our nice definition. And so that's what this last forcing is meant to do. It's meant to take all of this coding information that we'll get from the club shooting and the localization forcing and repackage it into a real. And so it's a version of Sachs forcing. So this is something called Sachs coding, actually, or coding with perfect trees. So what is it? So I need just a little more setup. Really almost done, I promise, with the setup. So assume the setting here is that we assume that V equals L of Y, where again, Y is a, it's a generic added by a cofinality preserving forcing. But more than that, I want to assume that it's actually a subset of omega 1. And we'll code Y into a real in the way that I will describe. So I need a sequence first of countable ordinals. So inductively define ui I less than omega 1. It's a strictly increasing sequence of countable ordinals such that for all I, mu I is least, which is greater, strictly greater than the sup of all the things that came before. Mu 0, this part is trivial. And two things happen. So the first thing, which is in Varensi's paper, if I look at L mu I of Y intersect I, it's a model of ZF minus. And then the second one, which is the only new thing we added to the forcing, though it ended up being very important, is that L mu I of Y intersect I is sigma 1,5 elementary in L omega 1 of Y intersect I. That's kind of surprising, I think, to find a 5 there. Yeah, so I will talk about this soon. The point is that basically we're going to be doing stuff that involves delta 1, 2, delta 1, 3, and then you want 1 or 2 more quantifiers sometimes. But just some remarks. So for the purposes of this first part, of this part here of the talk, you only really need this part. Why does such a thing exist? Well, essentially by condensation, there's a club of models that are fully elementary. So certainly you can find a mu I like this going all the way up. It doesn't need to be 5. It needs to be at least 5, maybe even 4, but I get nervous. If you wanted to preserve, we want to preserve pi 1,1 witnesses. If I wanted to preserve pi 117 witnesses, I would need sigma 117 plus 4 sigma 121 elementarity. The point is that you want to fix a finite level of the projective hierarchy, so you can actually write that. Like, I mean, this is actually something that's definable in L omega 1 of Y. And the last thing to note is that if V equals L of Y, then that structure L omega 1 of Y basically is the reals, right? I mean, every real is coded in there, and every element here codes a real, and all of the projective statements basically are kind of, if you like, sort of class theoretic statements over the structure. So this kind of makes sense. Okay, good. Why am I telling you about all of this? So I want to define basically I want to use this L mu I of Y intersect I sequence to define a collection of perfect trees that I can use to code Y. So just for simplicity, I'm going to write AI for L mu I of Y intersect I. And I do that in part because I think then you forget about all the nitty-gritty details of this, and you just remember there's some sequence of models here, and I think it makes it easier. and for the purposes of a talk, which is at 9 o'clock at night for me. Okay, so the last thing that I need is that if T is a perfect subtree of 2 to the less than omega, let the norm of T be the least I so that T is in A and this AI model. If I union up all of these things, I'll get L omega 1 of Y. And like I said, every real is in here. So every real appears in one of these. Perfect trees are reals. Okay, and we say a real R codes Y up to some alpha if for every beta less than alpha, beta is in Y if and only if. When I look at this A beta model and I append R to it, it's still a model of ZF minus. Okay, so it's a kind of nifty way to code Y using reals for countable segments. Right, the point is just that this is a countable transitive model. I can force over it. So those reals that you might force over it, that's going to preserve whatever fragment of ZF you have. Conversely, of course, I can find a real that codes the order type of all of the ordinals here in omega. I add that real to this model and I killed replacement, for example, right? So that's kind of what to think about here. And so my forcing C of Y, so I'll write the definition and then I'll erase my next board. So C of Y is the set of perfect trees T such that every branch through T codes Y up to the norm of T. Okay, so stare at that for a minute while I erase this board. And the order, I didn't say it, the order is obviously inclusion. It's like sax forcing. So I'll write it down in a second. If I force with this poset, I'll add a sequence of trees, and unsurprisingly, the intersection of them will be a real, the union of the stems, basically. And that will be a single real which codes Y all the way up. And this is what we want. But there's some things to say there. I might also mention, it's not immediately obvious, or at least it wasn't to me, why there is even one tree that has this property. But if you think about it for a second, and you look at the full binary tree, so 2 to the less than omega itself, that's obviously in A0. I mean, that's going to be in any model that has any amount of set theory. So that tree, I would only need that every branch codes Y up to 0, which is empty. Like, I mean, it's trivially true because there's no alpha less than 0. So the full binary tree is a condition. It's the maximal condition. Why there are any other conditions is not trivial. Okay. So fact. How long do I go to, by the way? Is it an hour and a half or 2 hours? What have we been doing? What have you guys been doing here?
I think an hour and a half is fine. That's our usual time.
Okay, awesome, cool. So, right. So three things. So first of all, T is in C of Y. If T is a tree in C of Y, then for all I, this is kind of awkward notation. For all I which is greater than or equal to its norm, I can find a T prime strengthening T, and the norm of T prime is I. So the norms of these trees go all the way up. Two, C of Y is proper and has the Sachs property. Three, this is what I said when I was erasing the board. If G is C of Y generic, and R is equal to the intersection of G, then this is a real which codes Y in the sense that for every alpha less than omega 1, alpha is in Y if and only if this model A alpha of R is a model of ZF minus. Okay, so we code Y all the way up. And I want to sketch two for you, this part here, not the Sachs property part, but this part here, because it shows you how it works, and it's just the kind of baby version of the preservation lemma that I hope I'll have time to say something about. So why is C of Y proper? So let theta be sufficiently large. M is some countable elementary structure of H theta. And I have some condition T, which is in M and C of Y. And of course, C of Y is in M. And I look at the Mostovsky collapse of M, so M bar. By condensation, this is equal to some L alpha of Y. Remember, V equals C of Y. This is equal to L theta of Y. Sorry, V equals L of Y, excuse me. And let's let delta be this omega 1. Some countable ordinal here. So I can construct this model. So this is, what's the point? This is equal to L alpha of Y intersect delta. I can construct this model in a big enough AI model. So there's some, in fact, it's going to be, sorry. There is some, I don't know, let's call it beta, which contains this model. Okay. And the thing to note, so A beta knows delta is countable. Okay. A beta knows delta is countable, so in particular, I can find some sequence delta n less than omega, which is in A beta, and it's a sequence. It's a subset of M bar, which is not in M. Okay. And essentially, what I'm going to do is I'm going to build a generic condition doing a kind of standard fusion argument basically, but work entirely inside of L beta. And this is going to, and then you'll see that this will ensure that I end up with a condition, because it's, it's clear that you can do fusion in the sense that you can preserve sort of larger and larger finite chunks of the tree, these end splitting nodes. But the intersection of all of those gives you a perfect tree. There's no way to know that it's actually in, that it's actually a condition. So I'm going to play a little fast and loose with the collapsed versions of things. So enumerate the dense opens dn of C of y. And inductively, so remember that for any n, if I have a tree T, let me maybe say this first. So T in my tree T, which is this condition, is an nth splitting node if it has two immediate successors, and it's the nth one, or yeah, it's the nth one in the collection of S that are less than T with this property. Okay, so the zero splitting node is the first place where you split. And then of course your tree goes up, and then you have the next split, it's perfect. So then I have my two one splitting nodes, and so on and so forth. And because it's perfect, you have 2 to the n many n splitting nodes for each n. And you write T prime as n below T, just in case T prime is a stronger condition than T. And we write it like this: the nth splitting nodes of T prime equal the nth splitting nodes of T. And it's sort of a classical fact that if you have a sequence like this, T0, T0, T below T1, T0, 0 below T1, 1 below T2, 2 below T3, it's called a fusion sequence, then the intersection is a perfect tree. So we want to do this same kind of thing here, and we need to just make sure that we end up with a condition at the end. So how is that going to work? We'll inductively define these trees so that and we'll do this whole construction. I mean, A beta has this model M bar, and it has enough set theory that it can talk about the model theory of M bar and talk about what M thinks, and it knows, it's not elementarity, it's not elementary in some big H theta, but it knows what M bar knows, and M bar is elementary. And so it can build this sort of fusion sequence. And we need to do it in such a way that the fusion ends up being the condition, the master condition. So, so I have my condition T, which I let be T minus 1. And then we have 0, T0, T1, where given Tn, let for each nth splitting node of Tn, find some S sub T, which is in M bar, so that it strengthens. I write it like this: if I go to the collection of elements of Tn that are comparable with this T, right? So Tn is a tree like this, and I have some T here in the n splitting node, and I just look at this tree sort of above there. That's my TNT. And I can find a stronger condition in M bar such that ST is in the dense open, that nth dense open, right? Because that's what it means to be dense. And the norm of ST is at least delta n. That was fact part 1 that I'm not proving. But M bar is elementary, it knows that you can do that. And then let Tn plus 1 be the union of the T of these STs. So the point is that, to go back to my picture, I thin out over here, I thin out over here, I thin out over here, and then I union them all up. So I have lots of different thinned out versions. So it's n below because I have the same splitting nodes. But now once I've chosen which one I go to, I know I'm going to be in the dense open.
Corey, these delta n's, are they cofinal in the
In
omega
delta,
1
yeah.
of the model? Okay, all right.
Yeah, sorry, did I not say that? That's what I meant.
I'm not sure, maybe I missed it.
I might have forgotten to write it. Yeah, they're cofinal. This is the point, right? And I can carry out this whole sort of recursive construction in A beta, which knows the model theory of M bar. All right, and now we let T infinity do that intersection. So I can write more if people want me to. This is kind of a standard thing in cardinal characteristics. Assuming that this is a condition, it's a master condition, because it's going to force that the generic will intersect the nth dense open inside of M bar. Is that okay for people?
Of course, yes, it's good.
All right. Good. So why is it a condition? Well, so T infinity is in this A beta, right? I constructed this whole thing inside of A beta. So its norm is at most beta. I'm sorry, I made a mistake here. Yes, I know that I made a mistake here. This actually is delta. It's not, this is explained in their paper. This is actually delta, sorry. You can make this be delta, and that's my mistake, sorry. So this is actually delta because it's the least, it's the least model that knows that delta is countable. And so we had one that knew that delta was uncountable, so it has to be below it. Yeah, sorry. So this is delta, right? And this is the point. So now, if I had a branch B, which does not code y up to delta, then so there's some j less than delta, so that j isn't y if and only if a of j of r is not a model of zf minus. So it breaks that coding. But the delta n's are cofinal, so so j is actually less than delta n for some n. And now the point is that because it's a branch through this smaller tree, it was actually a branch through Tn plus 1. And that's a contradiction because this one, by assumption, codes y up to delta n. So it can't have this happen. Okay. So this has to be a condition, which means it's a master condition, which is why it's proper. All right, so let's put this all together. So there's some bookkeeping, which I want to just not mention, but you have a sigma 1 definable bookkeeping function basically in L, the same way that you had the sigma 1 definable sequence of stationary sets. So this Fisher-Friedman forcing. So we'll call it P omega 2. It's an omega 2 length countable support iteration of S proper posets. And we're going to be considering over the course of the iteration reals that we want to sort of successfully code into a well order. And every real has a sort of canonical choice for its name, these nice names. So for every alpha, we'll define this sort of inductively with the definition. For every alpha less than omega 1, we can define less than alpha on the reals of P alpha. I guess I should write 2 to the omega here. By basically saying that X is going to be alpha below Y, just in case either the least gamma with X in VP gamma is less than the same for Y, or else they're the same. And remember, the ground model is L. The L least nice name for X is L below the same for Y. All right, and then L omega 2 will be the union of these L alphas. Of these, sorry, less than omega 2 will be the union of these less than alphas. So that will clearly define a well order of the reals on my eventual poset in the extension. But I need to show that what we're basically doing is we're coding successively this poset, this well order as we go along the iteration. So the way that works is the way that works is that we start out, we define this thing inductively. P0 will be the trivial poset and if P alpha has been defined, then P alpha plus 1, as always, it's P alpha star Q dot 0 alpha, Q dot alpha. At this stage, I could weave in something else if I want to. I'm going to avoid that for time reasons. So Q dot alpha is defined as follows. So first of all, if this sigma 1 bookkeeping function guess is, I mean, I'm just gonna say guess is garbage. Do nothing. And otherwise, suppose it guesses suppose that it guesses some pair sigma x alpha, sigma y alpha, which are nice P alpha names for reals. All right, so I have these 2 names for reals, and I want to sort of code that x will be less than y. And I guess I should say that I want that alpha forces that this sigma x alpha is alpha below sigma y alpha. So what do we do? Then Q alpha dot is itself 3 pieces. So K0 alpha star K1 alpha star K2 alpha, where first K0 alpha is club shooting to code X less than Y into basically the stationary, non-stationary pattern of my S alpha plus n less than omega. So I take this omega block of stationary sets, and basically I shoot. I can shoot clubs through just some of them to basically code X less than Y. These are reals, so I can code it by a single real and then code that into this. Okay. Then at the next stage,
you mean S omega alpha plus n, or
no, just S alpha plus n. I mean, I only need to do omega many things.
Okay, so you only do this at if alpha is a limit, or what? I mean, you need room.
Yes. Right? Yeah, I guess you're right. That's a good point. I mean, I don't know. This is how it was written in their paper, but it's not important. I mean, I guess I could even arrange for this. Where is it? I didn't write. I could arrange the bookkeeping so that happens. But yeah,
yeah, there's some at limit stages or something. Yeah.
Something. Yeah. Yeah. But yeah. Okay. Then my K1 is this localization poset for some phi alpha defined as follows. So first of all, my X alpha, basically it's a code for everything that came before. So it codes alpha, and it codes X and Y, and it codes the generic for what we had so far. And some other stuff that I think I'm going to skip. So it kind of codes everything that I wanted to code. And now phi alpha says the following.
Corey, could I just ask a quick thing? So when you use this localization forcing, this L of S alpha here, you showed before that that forcing is proper, but you argued in L of Y to show that, right?
No, I argued in L of G star, where G star was some arbitrary generic extension, which was cofinality preserving. So inductively, all of these forcings will be S proper of size omega 1, and we're working over a model of GCH. So
I see, but didn't you argue in the proof somehow that this elementary submodel collapses down to something of the form L alpha of Y?
For the C of Y poset, not for this one.
Oh, okay, that was the C of Y.
Yeah,
okay,
so basically what we're doing here is we're forcing that V equals L of Y. Actually, that's what this does.
Right. Okay. Okay.
Yeah. So phi alpha says that. Sorry, I think I thought I had 2 hours, so I know I'm running a little bit slow. So let me skirt over some of the details. Basically, it says X alpha codes. Basically, it says X alpha codes sort of everything up to now. And X less than Y is coded into the stationary, non-stationary pattern. Of this S alpha plus N. So basically, I just tell you what I did. It's sigma 1 because this thing is sigma 1. And so when I force with that, I get this, so essentially I get a subset of omega 1. That was the generic, right? I was building this characteristic function of a subset of omega 1. And on the evens, I coded X alpha. And I also sort of ensured that all nice enough models will sort of know that this happened. And I end up with the generic essentially being some subset Y alpha of, let's see, what is it? It's P star K0 alpha star K1 alpha. So this is So generic, and it's a subset of omega 1. And so now in the extension by this, now V equals L alpha, L of Y alpha, and we force with C of Y alpha, which is my K2 alpha dot. All right, and that's the inductive definition of this forcing. And what does it do? So theorem, and like I said, this is due to Vera and Psi. T omega 2 forces that sort of for all reals x and y, we get that x is omega 2 below y, this well order that we defined in no projective way at all, if and only if there exists a real r was added by one of these things. So that for all countable suitable models, if R is in the model, well, let's think for a second. So R coded Y alpha coded X alpha, and we had this property that if I have sort of a good chunk of X alpha in a nice enough model, then it knows about this stationary non-stationary pattern. So if R is in M, then M knows sort of X less than Y coded into the stationary non-stationary pattern. So existential quantifier, universal quantifier, being suitable, you need to say that it's transitive. And otherwise, this is just, arithmetic. Then remember, being the membership is pi11 in the codes. So an if-then statement is really either not this or this. So this is sigma existential statement again. And then this is arithmetic because it's just about what M thinks. So all in all, this is going to be a sigma 1,3 definition, right? Exists for all exists. And then, like I said at the beginning of the talk, because it's a well order, it's therefore delta 1,3. Okay. Do you guys mind if I just take 5 minutes to at least wave my hands at this preservation part of the proof?
Sure.
Sure. Yeah.
Okay, cool. So I'm not really going to be able to say as much as I would have liked to say about it, but the general idea is essentially it's tied up in this proof of properness that I gave. The point being that everything that I want to do, okay, so the only stage where I added reals was in C of Y, right? So a lot of these properness preservation proofs where you want to show that something nice happens, you only need to worry about sort of the successor steps, and then you have a general limit theorem. And because you can only sort of kill a lot of properties of ultrafilters, mad families, whatever, when you add reals, you really need to show that these things get preserved for the C of Y forcing. And so there's this sort of inductive step, but the point is that I need to sort of in order to run these fusion arguments that give you the preservation, you need to fit everything into one of those A delta models in such a way that A delta can compute enough information about your ultrafilter base or your mad family to actually run the argument. And this is where you're using absoluteness. So just sort of as an example, to say, so for example, we preserve what's called a tight mad family. I talked about these last time. Tight is just a strengthening of tight is just a strengthening of maximality that gets preserved by countable support iterations of proper forcings, roughly speaking. And it turns out that to say things like A is tight, or to say things like some element B is in the ideal generated by A, which is what you need to say. These things are sigma 1,5 if A is co-analytic, right? And so if I know that my model is right about sigma 1,5 statements, I mean, they're actually less than sigma 1,5, but if I know my model is right, if I know my A delta model is right about sigma 1,5 statements, then it knows sort of all of the relevant information about A, at which point I can run the sort of more standard preservation arguments. So the sort of strange thing about these proofs is that you really need, I mean, we only wanted to preserve definable witnesses, but it turns out you actually really need them, because otherwise there's no reason why the A delta model would have any relevant information about it, or even be able to say something about A. I mean, I can't stick A in one of these A delta models necessarily. It's an elementary submodel of L omega 1, basically. So I'm really kind of doing this on the level of sort of definable classes of these small models and ensuring that that makes sense because I've inductively made sure things are projective. So I think given that I'm sort of over time, I don't want to say more than that. But thank you so much for sticking with me, and I'm sorry I didn't get to more. Thank you.
Thank you. Very nice talk.
Thanks very much, Corey. That was really excellent.
Great, thanks. I'm glad you liked it. Are there any questions before we end?
I mean, I have a little question. So one thing that I kind of couldn't wrap my mind around was how this coding by whether or not these models A alpha adjoint any branch to the tree are satisfy ZF minus or not, how that works. Like how when you want to code that, you know, how do you selectively destroy ZF minus at some places and not at others? Can you, is there some way of thinking about that?
Yeah, sure. It's not so hard. So basically if you want to destroy it, I mean, you have a perfect tree, so you have a lot of room to code any other set you would like into a smaller perfect tree. So that will give you a branch that is bad. Yeah.
Mm-hmm.
And if you don't want to destroy it, if I think about that tree now as a forcing notion, it's co-enforcing. So any sort of generic branch through it will preserve ZF minus, and you can kind of take sort of a generic perfect subtree if you like, and you're good to go. This is the very, very rough sketch of the proof. This is what's going on. This is how you kill it or not kill it. Basically force or code something bad by purpose, on purpose. And you do it inductively. Does that sort of answer your question?
Yeah, I guess kind of. But maybe I have to go back there. So I mean, isn't it like, so you're not working in the same model, right? So you're looking at the sequence of these A alphas, and you want to make sure that. So for some of them. So, you know, what intuitively, what confuses me about it is like, it seems like I kind of think of these models as growing in somehow, like A alpha is somehow smaller than A beta or something like that. And then if I adjoin a real to the smaller model and destroy ZF minus there.
Yeah.
So how can I? No, let's say I preserve it when I add it to this real to the smaller model, but I destroy ZF minus when I add it to the bigger model. That's somehow counterintuitive to me that works.
I mean, okay, let me remind you of a couple things, right? So suppose I have T in A alpha, right? So T codes Y up to alpha if and only if for all beta less than alpha, and every, I guess it's not T, it's a branch B through T.
Mhm.
For all beta less than alpha, we get that beta is in Y if and only if, what is it? A beta thinks of B thinks ZF minus. But
Mhm.
I mean, even suppose alpha is in Y. Like even alpha, maybe B does not code Y up to alpha plus 1, right? And the point is that this happens frequently. Like you code it, I mean, you know, trivially, like it's easy to imagine, like I said, it's easy to imagine coding up to 0 and even like coding up to omega, it's not so hard. But right, at some point it becomes less clear. And then if you want to think about it, like I have, you know, A alpha plus 1 contains as an element, I mean, these are growing models and they contain as an element because I can construct it, A alpha. This one knows this is a countable transitive model it can force over it, right? So it can build a generic for any poset that's in here, in particular any tree, right? And that any generic like that will not be in this model, of course, right? And so it just needs to, like the inductive step is essentially, it needs to ensure that either you're going to take a subtree that does code that last point there, or does not code it, right? It just needs to be basically looking at a subtree so that all the branches either code, either all the branches either preserve ZF minus here or destroy ZF minus here, and either of those things it's easy to arrange. The point is that you have lots of branches that do both. This is kind of the argument.
Okay. Mhm. Okay, all right. Thank you.
One thing I should point out, a stronger condition doesn't mean a higher norm, right? Because you could imagine having sort of a complicated piece and a simple piece. And if I forced to go into the simple piece, then I drop down a norm maybe.
Mhm.
So then suddenly it became easier to deal with this.
Mhm.
Yeah.
Okay.
Yeah. I mean, Jensen used to give clever names to the combinatorial structures he built, like morasses. Does this kind of proceed? You called it a kind of forcing, or what name do you have for this generically for this kind of combinatorics, this kind of combinatorial object?
Sorry, I think I don't understand. What do you mean? What combinatorial object?
Well, you're building this thing, right? It's just, as I say, it's
Yeah.
reminiscent of a morass or something, you know. And you sometimes refer to it as a certain kind of forcing.
It is a forcing. I mean, I just defined a forcing for you, right?
Yeah. Okay. Okay. It doesn't, and it's really restricted to Aleph 1 and Aleph 2. You can't.
I mean, it's a poset that when you force with it over L, it adds a delta 1,3 well order of the reals,
Yes. Yeah,
while
that's-
preserving all of these other things.
Yeah. But it
Um,
seems to be a sophisticated machinery. I'm just sort of asking
Yeah, I
maybe
mean, like I
silly
said, this
question, but
this
can
part
it-
is not really mine. I mean, I didn't get to the part so much where we did new things, but this is Sai and Vera. But yeah, it's quite involved machinery. I mean, it definitely took me a while to get my head around it.
I guess Corey, just to explain what my confusion was, and I think I understand it better now. It was like, so if I destroy ZF minus in a more complicated model, so let's say alpha is less than beta, and I have a real that I add to a beta, and that destroys ZF minus there. My intuition was that if I add that real to a simpler model, that will also destroy ZF minus there. But that's not necessarily true, right? Because maybe the more complicated model has some real that in combination with the added real destroys it. But missing that in the simpler model, you still stand a chance that it might survive there. So I was kind of thinking of, maybe ZF minus is destroyed because the real that you add collapses something there or something like that. So anyway, that was my confusion, and I think I understand it better now.
Okay, yeah, cool. Good.
Okay. All right, any more questions? Nope, doesn't seem so. Okay, all right. Thanks for this nice talk. It was lovely to look at Blackboard for a change.
Yeah, it was excellent and made it slow enough that I could follow it. I was so happy.
Yeah, you go much slower when without slides.
Yeah.
Even though you do forget things. Yeah, well, thank you guys all so much. It was really nice to see all of you again.
Yeah, and it's a great format. I really enjoyed the talk. I mean, basically up to the end. I missed the detail here or there, but I got the big picture really well.
Oh, good. I'm really glad.
No.
Good.
All right, have a great weekend, everybody.
Yeah, have a good weekend.
Bye.
Bye everybody.
Bye.
See you in 2 weeks. Bye.